The second subject of our class today is called UDFs, or user-defined functions. So let's look at the UDFs. So what is the user-defined function? A UDF is a function, or is actually better to say programmed by the user, which is a program, a code written in C, the program coding language, which can be dynamically linked with ANSYS and to perform some predefined functions. So why program UDFs? Basically, in ANSYS, it has been improved over the years, especially in the recent years. In ANSYS, you have almost flexibility and inclusions of all the important models and methods that is existing out there and can be used for CFD, from different material types, from different viscosity types, different numerical simulation types, to physical models such as different turbulence models, radiation models, multi-phase models, so on and so forth. But always they have foreseen the possibility that some user wants to use something, wants to have a specific model, a specific material, a specific customized function, a specific execution on demand function, so on and so forth, or a specific solution initialization that essentially cannot be performed using conventional, already existing preset functions in ANSYS. For that reason, ANSYS has given us the capability to write our own codes, which from now on we will call them UDFs, and basically attach them to the ANSYS solver. So in this way, the possibilities are never ending for us to simulate anything that we desire. But since ANSYS is a commercial software, and understandably the code access is limited, and actually that, in my opinion, is one of the strong points of ANSYS, because if you work in this field long enough and you have experience with different codes, especially open source codes like Kiva or OpenFOAM, you will see that actually having everyone out there access to the source code would not benefit that much, because honestly it's gonna be a mess. So for that reason, the restricted access to the ANSYS source code is actually good for us. And since it is restricted, since it is there is no access to wherever we want to attach your UDFs, ANSYS has provided some injection points. So injection points are the points in the software that you can attach your UDF through that. Here what you see in here is basically the general layout of ANSYS code. You have the initialization, you have the different solution methods, your solvers, your material property, and so on and so forth. And the boxes in blue are the locations that you can inject the specific UDFs. For example, in initialization part, you can inject your user-defined initialization. In source term parts, you can have different source term added to the system, and so on and so forth. So we will be using this injection points if we need them to add any specific method or a specific function to the code. So one important thing to learn about writing a UDF is not the writing language itself, because first of all, it's a C and C++, which most of you have some sort of experience with it. And even if you don't, in this level of programming, it's very easy, because UDFs by nature are not very difficult programs to write. So one thing that you need to understand in order to write successful UDFs is the fluent or ANSYS data structure. How the philosophy works behind the data analysis in ANSYS. So, one big difficulty with writing a UDF is actually finding the coordinates of centers of cells and assigning to them whatever we want to assign. Because remember, at the end of the day, any function that you want to write the code for it and attach it to ANSYS, that function excuse me, that function has to be associated with a group of cells, right? With the cells that you have inside your domain. And if you want to associate a function with a group of cells, you essentially require the center of those cells. And by having centers of those cells, it basically means you should have the coordinates, XYZ coordinates of every single cell. Now imagine, even in simple problems, you're dealing with 100,000, 200,000, 300,000 cells, right? First off, including the center of coordinates for all those cells are near impossible. Second of all, even if you are assigning your function to a specific number of cells, even less, like 1,000 cells, finding what the cells are exactly in those domains and what are the coordinates is near impossible job. For that reason, Fluent data structure has included something called thread. So the thread is, you can imagine it as some sort of middleman in writing your code. So whenever you're writing your code, instead of writing it for a specific coordinates of the specific cells, you are writing it for a thread. So everything would be assigned to a thread. What the thread is a collection of cells. But once you are writing the code, you do not need to define what the thread is. It is just a collection of cells. Once you're done with writing your code and you attach your code to ANSYS and apply it in its right place, at that point, automatically thread will be assigned to the cells in that location. So in this way, it makes it very easy for us to write our own code because we don't need to know where exactly the cells are, what are the centers of coordinates, and so on and so forth. We have two types of threads, cell threads and phase threads, because cell threads are basic thing that we discussed, but sometimes you're not, rather than writing the function for the cells, you are writing it for some phases in your domain, which again, phase thread works same as cell thread. So in Fluent database, data structure, very simple. You have cell underscore t and face underscore t, which are basically the integer data type used to identify a collection of cells or collection of faces. And of course, you have boundary face, internal face. You can have nodes and so on and so forth. The definitions that we used to have previously. So all you will do once you define your thread, you will write down your function and you will loop over that thread, right? Because remember, thread is a collection of cells, right? So you will loop through it, meaning you will go through a loop that would assign that function or whatever your UDF is to every single cell in that thread. Let's explain it better with an example. Assume you have this bended pipe and the water flows from here, comes in and goes out from the top. Now, for your inlet velocity, instead of having a constant velocity or set of numbers, you have a function. So this function defines the velocity at the inlet of this pipe, and this is y direction, right? So the velocity changes by y. For this reason, we need to write a UDF, because if you recall, in boundary conditions analysis, in the inlet, velocity inlet boundary conditions, you cannot just directly go ahead and put this equation. So you need to write a UDF for it. So now let's look at the UDF and how it looks like. First off, on top of every single UDF, you have this library included, and this is very important. You have to include this library. This is called UDF.h, which is the library that includes all the functions, predefined parameters that you would need for ANSYS. Okay, without that you cannot use the thread, or you cannot use other future functions, or as we call the macros, that you can use in here. So remember, always and always define this. This is of course the name of your UDF, which will show up in ANSYS later on. So in here, what you would do is you will define your parameters, and over your thread, which we have defined it here. Remember, all we have defined here is thread as being a collection of cells. We have not defined what those threads are. It will be assigned later on once we go to the software. So you start looping, this is loop, over the thread, and in each iteration of the loop, you will go through these functions. Here what you do is f underline centroid. It basically goes and finds the center of cells for every single cell in the thread. Okay, and remember, f underline centroid is included in UDF.h. Then you assign a y to it, and based on f profile, and this is your function, you will calculate the velocity. As simple as that. So now that you have written your UDF, you need to attach it to the ANSYS. But before explaining that, I have to explain something, and this comes from experience. If you need to write a UDF, first and foremost, start searching on Google, because almost 99.99% of all the UDFs that you might need are already existing and is already written by someone. Of course, you might need to change and customize it for yourself. For example, the UDF for inlet velocity is existing, but of course you need to change the function. Okay, so you understand what I mean. So the general structure of the code is there, it exists. You only need to customize it for your own case. Okay, now when you have your UDF codes, whether through writing the code or finding a software and customizing it, now it's the time to attach it to the software. In order to attach a UDF to your ANSYS, there are two ways of doing it. You either perform something called interpreting or something called compiling. So in interpreting, what happens is you read the C code and interpret it, and the good thing about interpreting is you don't need a third-party compiler like C++ program on your computer to interpret the software, interpret your code. But the negative point is it will keep the whole code in your live memory throughout the simulation, and this will slow down your simulation if you are talking about a very complex UDF or you are talking about a complex simulation. The other method is called compiling. So in compiling, first off, you need a third-party compiler like C++ on your computer. Then first you will build the executable file and then load it. Here, as I said, it's mostly good for very complex UDFs or for heavy simulations. For us, specifically in this class, interpreting would suffice. So, already explained this, the pros and cons of interpreting and compiling, and always in this class you use interpretation, and of course, I mean, to be honest, 99% of the time, even in your project, you would not need to compile it, just interpret it. So, now that you have attached your UDF to your ANSYS software, you have one extra step to go. In this extra step, remember, you have just attached the code to your ANSYS software. It's not being used yet. The thread has not been yet defined. So you have to do that. So the next step is, okay, you know that what the purpose of your UDF is. Is it whether for inlet velocity? Is it a source term? And so on and so forth. So once you attach your C+ code to your ANSYS, now it's the time to assign the specific rule of that. So for example, if it is a velocity inlet, as it was in our previous example, you go to velocity inlet, you open the drop-down list, and remember, we always put on constant, right? And we provide a constant velocity for it. But now, in our drop-down list, a third option is added, and the third option would be the name of our UDF. Once you choose that, software will know, okay, the thread that is in your C++ means the cells at the inlet, and it has to assign the velocity on those cells using the equation you have provided. The last step, of course, is running the calculation. In this part, there is no specific change. You do what you do. If it's a steady state, you assign number of iterations and make sure it's converging properly. If it is transient, you will calculate time step size. You would assign time step size, number of time steps, also maximum number of iteration per time step, and perform the simulation as usual. There are many UDF hookups. It's not just about the boundary conditions or initial conditions. It can be about initialization, a specific method of initialization, or it can be about a specific way of reading a case, writing a case. It can be a specific instruction about the predetermined function to be executed at specific points. It is a wide variety of UDFs, so you can hook it up almost in anywhere in your software that you desire. Before we end this discussion, a second example. Here the example is, you wanna hear the example of initialization UDF. Here what you want to do is you want to initialize a temperature of 600 Kelvin inside a sphere with its center at 0.5, 0.5, 0.5 and radius of 0.25 and 300 kelvins throughout the rest of the domain. So inside of this sphere with the radius of 0.25 is 600, and everywhere else outside of this sphere is 300 kelvins. Here again, oops, sorry. Here again, you define your thread. You start looping over it. Then you find the center of each cell. Then determine if that center of cell is inside your sphere. If it is inside your sphere, you will assign the temperature as 600, else you will assign it as 300. All the functions that we are using here, the C underline centroid, begin underline C underline loop, POW, C underline T, so on and so forth, are called macros. These macros are basically predefined functions that perform specific acts, and they are all defined in UDF.h. So always remember to include UDF.h on top. Here I have just given you a quick list of most important ones, but remember, ANSYS has I think a 120-page user guide on the UDFs. So if you need any function more than that, you can go and find it there. Okay guys, this was our second subject, very short subject, where we will solve examples for it, and I'm sure it will be very clear for you. Thank you very much and have a good day.